Hey, this is Steven from the Green Engineers, and welcome back to my YouTube research series. So again, we have a little small research project here on 3D printing. So what we're going to look at is we're going to be looking at infill versus time versus weight. More so infill versus time. So if you're not familiar with infill, it is a pretty basic 3D printer property, which is basically how full is the part, how solid is the part. So a cool, unique property of 3D printing is that because you're building layer by layer, and you can't see the inside of your part when it's finished, you could pick whatever infill or however solid you want the part. So if you want to have a really nice lightweight part but still strong, you could lower the infill settings and get a really strong light part. If you want a more solid part, you could add more and more infill. But if you want to conserve plastic and you still want your outside shape, you could have the inside next to hollow. So let me show you how I did this test here. I was going all off Repetier Host, and Repetier Host was using Slicer. So my settings here was basically what I did is I kept it at 0.22 layer height, which we found out in the last video was the optimal layer height for time, and then I just took this at 5% increments, this bar here, after the override slicer settings, 10%, 15%, 20%, 25%, 30%, blah blah blah, all the way down. And infill pattern rectilinear, solid infill rectilinear. And let me bring up this guy really quick so I can show you guys what those settings are. But they're the same from last one, same from last time, and they're the same for each time. So I did 3 different cubes. I did a 2x2x2, it's 2 inch by 2 inch by 2 inch, and then I did a 1 inch by 1 inch by 1 inch, and I did a 3 by 3 by 3. So 3 inch cubed, 2 inch cubed, and 1 inch cubed. So here are my settings. 0.4 overrided to 0.22, 0.4 for layer height, 3 perimeter, 3, all of these checked, aligned, blah blah blah. Infill 15% overrided on the other one, combine infill every one layer, 0, 45, 70, blah blah blah. Skirts 1610, support material none. Perimeters 70, small perimeters 15, 50%, 80, 50, 40, 40, 40, 20, 150, 50%, blah blah blah. Max print speed. All of this is default, 225, default, with some retracts here, 5, 8, 5, 50, 2, checked. Alright. So yeah, just pick a slicer and pick 5%, 0.22. Just keep that the same. And then write down this number and this number. Okay, so I didn't mark this guy. This was the 3x3. This is the 1x1, and this is the 2x2. So this is the 3 inch cubed, 1 inch cubed, 2 inch cubed. All right. So if you see here, the 3 inch cubed is the one that has the biggest impact here. So if we look through here, we see that around 10 or so. Sorry about that. It's my cat. Around 10 or so, we start to increase in time. And you notice that the difference between here and here is only 4 minutes, and the difference between here and here is 36 minutes. So the difference between 5 and 10 is 22. So around 12% or so is your ideal for this guy. And you notice that if you increase the infill, the time it takes increases drastically. So we have pretty much a linear idea here on time. And then here's infill versus filament. We see that it's pretty much a linear relationship, and it's 1659 x. So no matter what your infill is, it increases by this much. At 0% or at 5%, it starts at this. So, you know, that's that's it's all pretty much linear. So as you see, there's no part where it like starts to increase. There's no part where like stays the same. It's a linear relationship. So that's kind of what I expected. Is that the more you add, it linearly affects the filament. And then here we notice that with this infill on the 1-on-1, it's 50 by X. So every time it's another 50 millimeters. Every time you increase the X. Here it's 466. So nothing out of the ordinary here. Nothing that I could really pull that's very interesting. It's just it's a linear relationship. I did think that maybe like from one layer to the next layer you're not increasing as much as like the difference between 50 and 60 is different than the difference between 40 and 50. But it looks like not the case. Because we do have some weird stuff here that we're going to go over. So all this seems pretty unique. It's pretty much linear for the most part. Our R is 1, so it's pretty much an exact, it's perfect. Because R squared, the closer you get to R squared being 1, it's perfect. And if it's 1, it's perfect. So this is a perfect line. So it's perfectly linear. There's no movement or anything like that. Alright, so yeah, here it seems that this is your best case. So usually when you do infill on a 3D printer, your average infill is 10 to 15% or so. And this, if you want a really strong part, you'll double it. But most of the time, 10 to 15 is your go-to. So here, so that shows up here is an ideal spot before you start to ramp up on time. And you see that and these are all in minutes. And you see that once you get to 100%, you're way up there. You're 863 minutes compared to 210. So that's 4 times. That's about 4 times the length of time. And also, this looks pretty linear as well. All right, here's the 2x2. Or this is not supposed to be 2x2. This is the 2x2. Forget what that says. Okay, so now that's right. Alright, so we see that here from 57 to 60, and this is the 1x1, so this is a really small cube. And then here, it doesn't really take, so I don't know if this is an error with the slicer, but it just kept giving me the same time, no matter what. So I'm wondering if to this point, it just doesn't take any more time to do. But you notice again that around 15, 10 to 15 is where it starts to hike up. So this is a different slope, and then this is a new slope. So right here is when you have the smallest increase in time. So again here 10 looks pretty good, because you have the least amount of increase between 10 and 15. So yeah, here again 10, because right after 10 you're hiking up. So here 15 would be fine, but right after 15 you're hiking up. And then if you get up to here, that's fine. So you see here with the numbers 560, 61, 63. So the difference between 10 and 15 is 1 minute. So you might as well go with 15. Yeah, so here 15 is good. So here 15 is good, here 15 is good, because the difference between 10 and 15 is only 1, and the difference between here and there is 2. So 15 is good here, and then of course anything after this it's so compressed that it doesn't take much time. It doesn't add much time to the printer to print that out. So again, 10 to 15 is good. And then here again in minutes, this is a 2x2, so 2 cubed, 2x2x2, so it's 2 cubed. And we see here we got another weird thing where this takes the same amount of time for some reason, and then it hikes up. And then here, if we look underneath, you'll see that that's where I entered in the This is a formula. It's hours times 60 plus the minutes. So Slicer was giving me a constant time. And then it starts to hike up. And we see here also again that the infill is linear. So here we're looking at between 0 and 40 or 35 is your ideal spot here for the 2x2. Which is weird because it's completely opposite of this guy. But yeah, I don't know why it's doing this, but I'm just gonna say that it's working correctly and that there's not some. It could be that a lot of this stuff is glitches. This here's a glitch. This here's a glitch. This here's a glitch. But in this case, again, 10 to 15 is good. 10 to 35 is good. So what I learned and what I could give to you from this little small experiment with passing stuff to Slicer and seeing what the time estimates give us, as long as you assume that the time estimates that they give you are correct, which they're usually not, is that the infill time change between one percentage and another percentage is, number one, not linear some of the time. Some of the time it is, and some of the time it's not. Number two is that it depends on what size part you have. And at some point when the difference between 20, 23 and the rest is no time change at all, just filament amount change. So, but from these three tests, and sometimes when you go past 3x3x3, you're getting close to some printers' maximum output. Some printers can do 4 inch by 4 inch, and most printers on the market do 5 by 5 or 4.5 by 4.5. So, and then better printers go higher and higher. But most printers, this is hitting the outer limits of what you can do. So it's interesting that if you keep looking at this, eventually this is going to go linear here. But the smaller the part, the less the infill has impact on the time. You see, between like almost zero, approaching 0 and 100 is 7 minutes. So something to think about. So from here, what I'm going to say is your best average time for each of these, for no matter what, is 10 to 15%. 10 to 15% infill will give you the best results for pretty much any given size. Now, if you're looking for strength, here it's 40, here it's 25, so here's 25. So yeah, 25, 30 would probably be your best all around look at infill for maximum strength for your time. So I would say 10 to 15, and then 30 to 40. So 10 to 15, 30 to 40 for maximum strength, 10 to 15 for average. And you could check these results out further by pausing the video and looking at the numbers, and then maybe coming to your own conclusion. But these are some very interesting results that will help you save some time while printing and getting the maximum quality you're looking for with a given amount of strength needed and filament that you want to use. So, but what I took from here is 10 to 15% average infill for any given size of part, 10 to 15%, and for maximum strength, 25 to 25 to 40 or so. 25 to 40 for maximum strength. Alright, that's pretty much it for this video, guys. If you guys like this video, please subscribe for more reviews like it and my research video series on the Green Engineers YouTube channel. And I will see you guys in the next video. Thanks for watching. Take it easy. Peace.